In the previous video, we graphed a polar curve by making a table of values. In this example, example 5.4.8, we're going to graph this function, r is 3 cos of 2 theta, not by making a table of values, but instead by referring to the graph of the cosine function. Which cosine function? This one. So we're going to imagine that we have a function in normal rectangular coordinates. R is 3 cos of 2 theta, and I'm going to graph that as if we had an r axis and a theta axis, r and theta. And we're going to use the graph of this function and translate that over onto polar graph paper to get an idea of what the polar curve looks like. So we know that this function is a cosine function, so it starts at its maximum. And we'll draw a couple periods of it here. So it comes down to a minimum, back up, and well, that's all that we have room for. So let's hope that that's enough. We know that our maximum is, because we're multiplying by 3 here, we're at 3. We know that normally the intercept is at pi over 2, but I'm multiplying by 2, so this has got to be pi over 4, which makes the minimum, which is going to be at minus 3 at pi over 2, and so on and so forth. So here we're going to be at 3 pi over 4. Our maximum will be at 3 again at pi, and this makes us 5 pi over 4 for here. All right, so we are going to use this. We're going to use this information to plot arcs on this graph. So when we start at theta is 0, when theta is 0, we're starting at a maximum. So if we're thinking about being here, we're right here at this point. And then what happens between there and pi over 4, we go from our maximum value down to a radius of 0. So let's go and add in pi over 4 here. There's the angle of pi over 4. And as we swoop in, I didn't notice that that turned itself into a straight line. Let's fix that. As we swoop in up from an angle of 0 to an angle of pi over 4, the radius is going from its maximum down to 0. So instead of swooping up here, the radius is going to swoop in and become 0. So we can go and graph that arc there. Now, what happens from pi over 4 to pi over 2? From pi over 4 to pi over 2, which is on this part of the circle, we go down from 0 to our minimum, negative. And we have to remember what that means, that graphing a negative radius, right? So if I were going to try and graph the point minus 3 and pi over 2, I have to go up to pi over 2 and then graph the radius in the other direction. So what does that mean? We're starting here. Let's add some color. So on this arc here, we are going from pi over 4 to pi over 2, but the radius is getting bigger and negative. So as we swoop here, the radius is going to get bigger and negative down here. And so we're going to get to a minimum of minus 3 at what point? Pi over 2. That puts us here. And so we're imagining this arc swooping out like this and getting bigger. And we continue in that fashion. So what happens from here to 3 pi over 4? We're going from our minimum, negative 3 up to 0. On the graph from pi over 2 to 3 pi over 4, so let's add it in 3 pi over 4. That's here. That's the angle of 3 pi over 4. And I added it down in this quadrant because our radius is negative. So we're going from this part back to 0 as we go along here. So that means we're adding this section of the graph there. And you can kind of imagine what's happening. We fill out, we're going to end up by having, so we've got this lovely arc happening. It's going to continue here and there. So let's do a couple more and we'll see how this ends up by looking. So let's go into orange from 3 pi over 4 to pi. Well, now we're back into positive radius. So from 3 pi over 4 to pi, we go from 0 to our maximum. So from 3 pi over 4 to pi, it looks like Greg put it in the wrong place when I used the neon highlighter. It's going over to here. So from here, we're going from 3 pi over 4 to pi, and our radius is going from 0 to 3. So we're going to get this kind of shape on the graph, which corresponds to this arc here. And maybe you can see where this is going. So from pi to 5 pi over 4, pi to 5 pi over 4, 5 pi over 4 is here. We're getting this part of the graph here, right, as we go from the maximum radius down to 0. And so there's one part of the graph left to fill in. You should, well, there's a couple little segments here. You should hopefully being able to imagine what's going to happen along the next sections. We're going to come up here and back down. And then lastly, we will end up by filling in this part here when we start the whole process again. So this is an example. It's quite a pretty example, I think. It's an example of a polar curve called a rose, although it's not really rose-like. It's more sort of daisy-like. It's got petals, but it's called a rose. It's like a flower. And there's tons of examples by playing with whether it's sine or cosine and what this multiplier is in the middle. You can get all sorts of crazy zany flowers going on, and well, not quite like that, now I'm exaggerating, but all sorts of beautiful flowers in the middle. You don't have to know exactly what you get by how, but this technique of plotting arcs from the function graph and plotting them onto the polar graph paper is a technique that you should practice doing to be able to graph different roses when different equations are given to you. In the next video, we'll see one more kind of polar curve, and then we'll do a summary of the polar curves we've seen so far.